In this video, we're going to discuss the structure of the atoms, okay? And more specifically, we're going to discuss three subatomic particles: electron, proton, and neutron, okay? All right, let's take a look at this slide. This slide shows us the discovery of the electron, okay? This is a very famous experiment done by Joseph Thomson around 1897. Okay, this is his experiment. I noticed one thing very interesting. Okay, during his research. Well, this is a high voltage battery, and this is a tube, and it's under vacuum, means you have to remove air particles or air molecules away from this tube. Okay. And on this side, you have cathode, which is negatively charged. On this side is positively charged anode. And once you apply the high voltage, he observed some particles flew from a cathode to anode, and he called it a cathode ray. Okay. Later on, of course, this cathode ray actually is a beam of electrons. Okay, so this is how the real equipment looks like. Well, he discovered electron, and with more research, he identified the mass and the charge of electron. Okay, the mass of the electron is very, very small, right here at the bottom of this table from your textbook. Okay, and the charge is also very small, and also it's negatively charged. Okay, one thing I want to mention here is, well, this is the real mass of an electron, and here this is a mass in AMU units. Okay, what is the AMU? Well, AMU is called atomic mass unit. It is defined as 1/12 of 1 carbon-12 atom. Okay, so if you take the ratio of the mass of 1 electron over the mass of 1/12 of carbon-12 atom, then you got this ratio. Okay, this is actually a ratio. But anyway, this mass in AMU of those three subatomic orbitals is not our major concern, okay, for now. What you need to know is the mass of an electron is very small, and it is negatively charged, okay, because this charge is very, very small. So sometimes we use -1 or 1 negative to represent the charge of 1 electron. All right, this is electron. Proton and neutron. Okay, those two particles were discovered by Rutherford and Chadwick. Okay, those two pioneers. Well, for protons, it was discovered by this gold foil experiment done by Rutherford around 1911. Okay, so what happened in this experiment is the Rutherford used alpha particle to bombard the gold foil here. Okay, and around the gold foil there is a ring, and this ring is actually a detector. Okay, so alpha particle comes from here, this box right here, to bombard the gold foil. By the way, the alpha particle actually is helium, high energy helium atoms. Okay, all right, so what he discovered from this experiment was the alpha particle can pass through this gold foil and reach the other side of the gold foil, okay, this area. But some of the alpha particle get deflected by this gold foil and reach this area and this area. Okay, so that tells us some very important information. By the way, for alpha an alpha particle is positively charged. Okay, let me put a positive sign here. So it's positively charged. All right. So this Rutherford experiment tells him actually some very important information regarding the structure of atoms. Okay. And of course, he did some more research. Chadwick did more research, and altogether, they discovered the proton. Okay, right here, the mass again, it's very small, but but when you compare the mass of one proton with mass of one electron, the mass of proton is much higher than mass of electron. Okay. Keep that in your mind. And proton is also charged, and it is positively charged. And this is a charge coulomb. The capital C represents coulomb, the charge, the unit of charge. Okay, so it's positively charged, and when you compare the charge of proton and electron, you can see the only difference is proton is positive charged, electron negatively charged. The charge itself for proton and electron is the same. Okay, so that's why you see positive 1 or 1 plus for a proton and 1 minus or negative 1 sometimes for an electron. Neutron, the mass is right here. Again, when you compare the mass of neutron and mass of electron, neutron is much heavier. Okay, and the neutron is neutral. And that's how it gets its name, the prefix NEU. Okay, so it does not have a charge. We label it as 0. Now, one thing I want to emphasize here in this table is you can see that when you compare the mass of proton, neutron, and electron, proton, neutron are much heavier than electron. Okay, so later on when we discuss the atomic structure, okay, this information will help you understand why some of the particles get reflected. And actually, we can take a look at this graph. Okay, this graph is the proposed atomic structure based on the Rutherford experiment. What happened here is this thing, the yellow cloud, and this tiny thing here, that is a gold atom. Okay, pure neutral gold atom. And in the center here, this tiny thing here is called the nucleus. And this yellow cloud around the nucleus is called the electron cloud. That means you have multiple electrons moving around the nucleus. So what happened here is these black lines, they are alpha particles. Okay, as you notice that most of the alpha particle just pass through the electron cloud. And so this side is the detector, okay, remember? So that is why most of the particle, alpha particle, just pass through this gold foil and reach the other side, the opposite side of this detector. But some of them get deflected. The reason why most of the alpha particles can pass through is the size of the atom, the size of the nucleus. When you compare the two, the size of a nucleus is much smaller than the size of an atom. Okay, let's give you an analogy here. If you said that the UCA campus is an atom, then and the size of a nucleus is pretty much like the size of your bedroom. Okay, so so that means for an atom, the majority or the most part of the atom are empty. So that is why those alpha particles can pass through. And you may ask me, well, you said that electrons are outside the nucleus. So what if those alpha particles, collide with electrons? Well, that won't be a problem because alpha particle is very heavy, and those electrons are very, very light. So even if you have light electrons interacting with those heavy alpha particles won't change its moving path. Okay, so that's why it reached the opposite side of the detector. But how about those alpha particles get deflected? It's because when you have one alpha particle, for instance this one, just hit on the nucleus right on the spot, because nucleus, okay, it has protons inside, okay? So the nucleus is positively charged. And as I mentioned a moment ago, the alpha particles are also positively charged. Therefore, you know, the positively charged particle, they don't like each other. That's why this alpha particle get deflected, okay? And that would be this one here. And you know, for some other particles, alpha particles, they just hit the nucleus not right on the spot, but just glide that slightly, so it goes this way and just go this way. Okay, it turns to the its moving path with an angle in this case. Okay, so this is the some information, some ideas about the atomic structure based on Rutherford experiments. All right, and based on Rutherford experiments and Thomson's experiments and some other experiment evidence, Bohr proposed the first model of atoms. Okay, so basically, this is an atom, and you have electrons. Those red dots here are moving around the nucleus, and the nucleus, it's very small. Okay, and you know, as I mentioned in the previous slide, most of the weights of an atom will be on the nucleus, okay, because the mass of electron is so small. And so the nucleus has protons and probably neutrons, okay, based on what element you are talking about. Okay, so so you know, sometimes you see a textbook or you know website use the structure of our solar system as an analogy of the atomic structure. Well, it won't hurt for you to do such a comparison, but the structure, the atomic structure, is not that simple. Okay, so for instance, those electrons are moving around nucleus, and that's for sure, but they are not following this kind of type of orbital. And actually, electrons are moving around nucleus through the speed of light, very close. So the movement of the electrons are quantum states. Okay, so this moment the shows up here. Okay, and next moment they just show up here. Okay, so it's not this kind of simple movement along the orbital. All right. Now, in the next few slides, I'm going to show you how we use these three particles, subatomic particles, to help us understand the elements and the chemicals better. Okay, let's start from protons. Well, in chemistry, in science, we use protons to define elements. Well, in order to explain this, let's use this periodic table as an example. Well, this periodic table, for each box, it has 3 pieces of information. Okay, the first one here for the beryllium, 4 on top. Well, that is atomic number. We use the capital Z to represent atomic number. What is atomic number? Well, atomic number Z is the number of the protons. Okay, number of protons. So for instance, the atomic number for beryllium is 4. That means beryllium has 4 protons. Hydrogen, because the atomic number is 1, that means hydrogen has 1 protons. Okay, for copper, you can see that atomic number is 29. That means for copper atoms, each atom has 29 protons in nucleus. All right, and if you take a look at the overall picture of this periodic table, the whole periodic table is organized by the number of protons. In other words, atomic number: 1, 2, 3, 4, 5, 6, and so on. Okay, so if somebody tells you an atom has a certain number of protons, you can come to this periodic table and identify what the element is. So that is why we said that protons can be used to define elements. Different elements will have different number of protons. All right. Was about how we use protons to find elements. Okay, here on your left side, it's helium. Okay, helium balloon here. It has a lower density than air, so that's why the helium balloons can fly. Anyway, so for helium nucleus, it has 2 protons. And on your right side, it's carbon. Well, for instance, the material you used in pencil. And carbon has 6 protons. And apparently, you can see that different elements will have different number of protons. All right. The next thing is about isotopes. Okay. Before we talk about how we distinguish isotopes, let's define isotopes. Okay. Let me write it here. Isotopes are atoms with the same number of protons. I'm going to use P to represent protons, but different number of neutrons. I'm using lowercase n to represent neutron. Okay, so this is how we define isotopes. Well, let's use hydrogen as an example. Well, hydrogen has 3 isotopes: protium, deuterium, and tritium. And what's the difference among the 3? Well, for protium, it has only 1 proton inside and 0 neutron. Of course, it has 1 electron outside to balance the charge to make the hydrogen atom as neutral. Okay, but for deuterium, it has still 1 proton in nucleus, but now it has 1 neutron in the nucleus also. Okay, still it has 1 electron. The hydrogen atom for the deuterium atom, it is still neutral because neutron is neutral, right? So 1 proton, 1 electron, the charge is still balanced. Okay. Now the third isotope for hydrogen is tritium. It has 1 proton, but now this time it has 2 neutrons inside nucleus. Okay. Again, it is still neutral because 1 proton, 1 neutron get cancelled. Okay. And here, these are the natural abundance of those 3 isotopes. As you can see, the dominant isotope for hydrogen is hydrogen 1, protium, and the tritium is just so small, the natural abundance. Okay. Another example about isotopes is carbon. Well, carbon 12. Okay, we'll see why we get the 12 here in a moment. But carbon still has 3 isotopes: carbon 12, carbon 13, and carbon 14, and these are the natural abundance of those 3 isotopes. Okay. Now we need to specifically explain what this is. Okay. Well, we know that for one element, it may have multiple isotopes. Then how do we distinguish the isotopes? How do we symbolize the isotopes? Okay, we need to use a notation. What kind of notation? Well, let me write it here. X. The X here is the chemical symbol. Chemical symbol. Okay, it's like a hydrogen H, carbon capital C, boron capital B. Okay. These are the chemical symbols that can be identified from periodic table. Now, on the left side of this X, superscript, capital A, this is the mass number. Okay, and subscript, Z. We talked about Z already in the previous slide. It's a atomic number. Atomic number, that means number of protons. Okay. Now, what is this? What is the mass number? Very simple. I'll write it here. Mass number actually is the number of protons plus number of neutrons. Okay, very straightforward calculation. But by doing this, we can symbolize the different isotopes. Okay, because we do consider number of the neutrons. Now let's apply this notation on carbon in this case. Okay, so for carbon 12, let me write it here. For carbon 12, this is a chemical symbol, and you have 12 right here. For carbon, we know that atomic number is 6 protons. So we write 6 here. Okay, so when you have this carbon 12, that means for this particular isotope, you would have 6 neutrons. How do I know? Because remember, this is the sum of number of proton and the number of neutron. So if you use 12 minus 6, that equals to 6. So that means you have 6 neutrons. Remember, this 6 is this one. Okay, so that means it's 6 protons. So mass number 12 minus 6 protons, you have 6 neutrons. All right, let me label it here, 6 neutrons and 6 protons. How about carbon 13? Okay, we know, again, carbon 13, we are talking about the carbon element. It still has 6 protons. Now this time, 13 minus 6 protons, that equals to 7 neutrons. Okay, so this one has 6 neutron. Sorry, let me erase this. Would have 7 neutrons, still 6 protons. Carbon 14, again 6 protons. Now this time 14 minus 6 protons equals to 8 neutron. So 8 neutron for carbon 14 and 6 protons for carbon 14. Okay, so again, 3 isotopes, same number of protons but different number of neutrons. Okay, so that is how we use isotopes to define. That's how we use neutrons to define isotopes. Okay, all right. Well, one thing I do want to mention here is sometimes in order to make things simpler, instead of showing up the protons, sometimes we can ignore them. In other words, for this notation, I can just simply write it that is a carbon 12. Okay, for this notation, I can write that as simply as carbon 13, and this one here simply as carbon 14. Okay, the reason is, if you know the chemical symbol already, you know the atomic number automatically, because you can find out the atomic number from periodic table based on the chemical symbol. So the Z and X this is redundant. Okay, so you can sometimes when you write the isotopes, you can ignore Z. All right, these are the isotopes. Well, let's do some quick practice. Identify the number of protons and neutrons for the following isotopes. First one, uranium-234. Well, how do we deal with this problem? Remember, uranium-234, let me write it here, 234. Well, the number of the protons of uranium can be identified from periodic table, remember? So let's go back to the periodic table we had. Okay, if you take a look where that uranium is, it's right here. Okay, it is labeled as 92, so that means it has 92 protons. Okay, so ideally it should be right as U92-234. Now with this information, it's very easy now, because proton we know that is 92, sorry. And now the neutron, that should be 234 minus 92. Okay, that would be 142 neutron. All right, so first example. Now the second example here, boron 10. And boron, we know, if you again go to periodic table, it will have 5 protons. So for boron 10, proton 5, number of neutron equals to 10 minus 5 equals to 5. Very simple math, but you do need to know how. Okay. Now the last one, krypton. Again, go to periodic table. You will see that the krypton has 36 protons, since it's 84. Okay, so proton 36. Then for neutron would be 84 minus 36. That will give you 48. All right, very simple math. This is isotopes. Now, electrons. What do we do with electrons? Electrons can be used to define ions. Okay, let's use this example first. Okay, so this example shows you one atom lose 1 electron. What will happen? Well, if you take a closer look of this atom here, 11 plus tells you that the nucleus has 11 protons. 11 protons. So based on what you can find on periodic table, this actually would be sodium. Neutral sodium atom. Now, if you count the number of the electrons, these negative charged dots, it has 11 electrons. Okay. Now, since the 11 electrons, negatively charged electrons, and 11 positively charged protons, they cancel each other out. So this is a neutral sodium atom. Now, if you can use a chemical method to remove one of the electrons, okay, you will generate a new particle. In this new particle, the nucleus still has 11 protons, but now you have 10 electrons outside. Okay. Now you consider the charge of this new particle. You have 10 negatively charged electrons and 11 positively charged protons. So 10 electrons can be cancelled by 10 protons, but you still have 1 positive proton in the nucleus. So that will make the whole particle have 1 positive charge. If you write this down by using a chemical equation, that would be something like this. Neutral sodium atom lose 1 electron, and that will generate a sodium cation. Okay, sodium cation. This positive sign comes from that 11th proton. Okay. All right. Of course, if you lose 2 electrons, then because now you only have 9 electrons outside this new particle, you have 11 positively charged proton in nucleus. So this is going to be sodium 2 plus, because you would have 2 positively charged protons that cannot be cancelled by electrons, because you simply don't have enough electrons to cancel these 2 protons. Okay. All right. Of course, later on you will see that it's going to be very hard for you to remove 2 electrons from sodium. Most of the time in chemistry, you can only remove just 1 electron to generate the sodium cation, sodium 1 plus. Okay. All right. Now let's take a look at the second example. This is the chlorine. How do I know it's chlorine? Because it has 17 proton inside this nucleus and 17 electrons outside nucleus. So this is a neutral chlorine. Let me write it here. 17 proton, 17 electron. Again, this is neutral. Okay. Now, if you provide 1 electron from somewhere, we don't know. Okay. So you have we don't need to care about where this electron comes from. Okay. That's not our concern. What we know is if you provide 1 more electron to this chlorine atom here, you are going to generate a new particle. Okay. So in this new particle, if you count the number of electrons, then you will have 18 electrons. 18 electrons. And you will still have 18 protons inside. Oh, sorry, 17, my bad. 17, okay, 17. Now, as you notice, now you have one more electron in this new particle. And that will make this whole new particle negatively charged. So again, if you want to write the equation, that would be chlorine obtains one more electron. It generates chloride, Cl minus, okay? Because that minus, this minus sign comes from this extra electron, okay? Of course, if you provide 2 electrons, then that will be chloride and two negative. Again, this type of reaction is going to be very, very hard. Most of the time, chlorine will just accept 1 electron to generate the chloride. All right. So this is the video. We need more practice. If you have any questions, you let me know.